By the end of these two videos, you should be able to solve things like this, or know the value of this, without using a calculator. You'll also be able to solve identities or prove identities like this, involving sine x plus y, cos x plus y, and tan x plus y, also the negative equivalents of those. And you'll finally be able to recognize what cos 2x is expanded, and sine 2x, and tan 2x. Okay guys, so this video we're going to talk about the addition formula and proving the addition formula. The reason why I'm putting emphasis on it is because we're going to be using this formula throughout your C3 trigonometry and in your C4, but also it proves where the double angles come from, which again are really important to your studies. So I think it's worth taking some time to figure out how this addition formula was derived. And you know, if you don't understand the proof, that's okay, it's alright, but it would be nice perhaps for you to try to appreciate where this stuff comes from. The main one you need to know, and you do need to commit these to memory, yeah? This is cos A minus B is always equal to cos A cos B plus, so the opposite sign to that in the bracket, sine A sine B. There are 4 identities in total, 4 addition formulas I suppose you could say, but all of them, the other 3, will stem from manipulation of this one. So if I prove how this one came about, I can then start proving the others. So let's do this then. So I'll put that there. The way to start this is to look at, because of course we're looking at triangles really, aren't we? So if I call this point P, and draw another one, this one point Q, here, and I put these on a circle of radius 1, so that's 1, yeah? This angle at Q, well, leading up from Q and the x-axis here, is the angle B, and then this large angle must be the angle A. And I can denote, well, draw my distance between P and Q by this straight dotted line here. So this is where it's going to start, guys. What we're going to do is we're going to look at the cosine rule first, and then compare that result with looking at it in another way, yeah? And then we can figure out, by comparing the two, what's going on, and therefore prove the final formula. So, minimize that. Let's do it. So, we'll start with the cosine rule. So, from the cosine rule, I can tell you that PQ squared, equals 1 squared plus 1 squared minus 2 times 1 cos, and then obviously this angle is the one we're talking about, so A minus B. So therefore PQ squared equals 2 minus 2 cos A minus B. This is our first major equation, right? I could also look at this a second way then, in order to compare it to my cosine result. Okay? I could say that Q must be the coordinates, so Q must give coordinates. Well, since we have this angle here, this is Q, and this is our angle B. If I drew a right angled triangle with this, I can say this is 1, therefore Q has x coordinates cos x, and it has y coordinate sine x, except it's not x, it's our angle B, so B. Similarly with P, I can say that I have angle cos A, well, for my x coordinate cos A, and sine A, right? So now, using my distance formula, I can say that the distance PQ squared, so normally PQ equals square root, so if we square both sides, I can say PQ squared equals, from Pythagoras, sine A minus sine B squared, so that's y2 minus y1, plus cos A minus cos B squared. If I expand those brackets, I get sine squared A minus 2 sine A sine B plus sine squared B, and then expand this one, plus cos squared A minus 2 cos A cos B plus cos squared B. Now if I start grouping this stuff together, so if I group sine squared A plus cos squared A together, so that is this and this, and then group together my sine squared B plus cos squared B, so that's this and this, and then I'm left with minus 2, take the factor of 2 out, sine A sine B plus cos A cos B. So this part here is equal to 1 from our identity, sine squared plus cos squared equals 1, and this bit must equal 1. So then I can say that this thing, actually PQ squared equals 1 plus 1 minus this thing, so that's 2 minus 2 cos A cos B plus sine A sine B. So this is my second equation. My first equation told me that PQ squared equals 2 minus 2 cos A minus B. So since these two are the same, if I compare these two results, I can see that actually this thing must equal this thing. So therefore I've proved that cos A minus B is always equal to cos A cos B plus sine A sine B, which is our first major identity, and therefore addition formula. So now I've proved that this main result here, as I said, I can start proving the other ones. So let's look at identity 2 then. I want to find out what cos A plus B is. So I can use my previous result to find cos A plus B by taking cos A minus B. Do you see? This would make this work by using this formula, so I can say that B is actually minus B. So if I put this into my formula, this means that I have cos A minus B equals cos A cos minus B plus sine A sine minus B. So therefore I have cos A plus B is always equal to cos A cos minus B, because cos is an even function, is still cos B, yeah? Whereas here sine minus B is actually, because it's an odd function, f of minus x equals minus f of x, so therefore this would give me a minus sine B. So therefore I have minus sine A sine B. So that's our second identity and our second addition formula proved. Okay, and from this second result, the causes were quite easy, but now we need to find out the sine version of these. So from the second result, I can find out the sine version of sine A plus B. And the reason I can do that, or the way I can do that, is to recognize that cos A plus B minus 90 degrees is actually the sine A plus B graph, because we know that cos A looks like that, right? And if it's shifted by 90, if it's translated by 90 degrees towards the right, we actually get the sine graph like so. So it makes sense that cos A plus B minus 90 is actually the same as sine A plus B. So therefore, I can use my result, but instead of having B, I have B minus 90 in my formula here. So let's do that. So I get cos A plus B minus 90 degrees is the same as cos A as normal, cos B minus 90 this time, minus sine A as normal, sine B minus 90 this time. So from here then, the whole point of this is sine A plus B, which is equal to cos A. This cos B minus 90 is a shift of the cos graph, which, as we said earlier, is sine B. And then I have minus sine A. Then I have minus sine A as normal. And in this part, sine B minus 90, or if I think about that, so here I have the sine graph, yeah? Then if I translate it by 90 degrees to the right, I actually get the graph of minus cos x. So minus sine A times minus cos B. So that implies that sine A plus B is always equal to, this is now positive, right? So I can say sine A cos B plus cos A sine B. So that's our number 3. So again, taking that last result, I can now find, similarly to the cos versions, I can now find sine of A minus B by putting this as, this is sine of A plus minus B, replacing, so we get sine A as normal, cos minus B, plus cos A as normal, sine minus B. So this would be sine A minus B is always equal to sine A cos of minus B, even function, stays the same. This time though, sine of minus B, odd function, makes it a minus sine B, so I get minus cos A sine B. And there we go. There are my 4 main identities involving cos and sine. Now I need to prove the tan versions of these. And as well as the tan version of these, I can then give you all the double angle formulas and where they come from. So we're going to see that in the next video.